an interesting, larger challenge than what we were initially thinking of, but still doable.
Right. But because it's been made project specific, it's not generic in the universe proving everything under the sun. It's for this particular pipe, for this specific load case. Those applications.
Questions on this? If not, we'll go to the next one. This slide basically shows our major sections of this middle. We'll be identifying the components, the material inspectors, material inspections and controls. The design basis, with drawings, calculations, our design specification. Installation, our sample procedures, examination and testing, our quality control program, qualifications and testing will be there. OE, operating experience, and in-service inspection, what we plan to do.
I'm guessing you're going to go through all of these as we get to effect.
Yeah, high level.
Yeah. So each one of these sections pretty much outlines the 50 or so slides that we have within the presentation remaining in 50 minutes.
All right.
We're getting there.
Please proceed.
So we've already talked about this briefly, but just to make sure we're all on the same page, when we say CFRP, that is carbon fiber reinforced polymer composites. And we refer to the CFRP lining or the CFRP repairs. That's because that's the major reinforcement system. A subset within the CFRP repair is we also are using GFRP, or glass fiber reinforced polymer composites, a different type of fabric that's used for non-structural purpose for the first layer that goes in contact with the steel as what's called a dielectric barrier, because carbon fiber has a potential for electrical conductivity. The epoxy serves as an isolator, but the glass layer provides a definitive barrier so that you avoid any potential for galvanic corrosion. And then the glass also serves as a water tightness layer. So when you have a laminate sequence, and Roscoe will get into this further, you want to make sure you don't get any leakage through the lining system itself, and that serves to ensure water tightness. And he'll get into some of the testing that's been done to verify that. You can see here at the very top right picture, that shows the raw carbon fiber fabric that would show up on the job site, which comes in a roll, typically several hundred feet long roll, and then it's going to be ran through what you see in the bottom left, which is a mechanical saturator. The 2-part 100% solid epoxy is mixed, and then there'll be baths where the epoxy is able to impregnate and saturate the carbon fiber fabric. The drum rollers will be calibrated to the specific VRAP carbon fiber system being used on the project, and then we would do special QA/QC checks to verify the weight ratio or the amount of epoxy being added to that fabric. Here you can see on the bottom right the actual materials being laid up on the inside of the pipeline. Those would have been cut specifically to length, all done by skilled technicians that have gone through our qualifications and training program. For sake of time, I'll just let you know that here you can see a list of the different types of materials that would be used on the project, which includes saturating epoxies, an initial primer layer on the pipe substrate. The epoxy is also added with a thickening agent, so in between each layer, almost a consistency, almost like peanut butter, to make sure that you fill in any little surface voids and that you get intimate contact between layers. There'll be the structural reinforcing fabrics, which is the carbon fiber, the unidirectional layers, and non-structural glass fibers. It's important we're using unidirectional fabrics because that serves as almost like the rebar cage. So the reinforcement goes in the direction that you would need, either longitudinal or circumferential. We'll have a thickened epoxy top coat, and then there'll be, at the end, there'll be special termination materials, expansion rings as well.
All these procedures and the QA, are they going to be the same for regardless of the size of pipe or?
So the application procedure is the same for all the different pipe geometries. Some of the nuances in terms of the application processes may be a little different. For the larger pipes, you'd end up with access platforms to allow for full 360-degree access to the pipe. For the smaller diameter pipes or the laterals or manholes or whatnot, sometimes you'll be working your way back towards an exit. But that's more means and methods, and we would be making sure that that's all covered with the appropriate language to ensure proper installation is within the procedures.
When we do repairs for the cause,
through this, because we got...
What the holes that are left.
There are special detailings to accommodate that.
Right.
So we would make sure that there's development length and appropriate detailing.
What I am seeing by looking at this right now and the level of interest that we have and the level of difference from the regular piping system, that I think, as far as this relief, I'm going to recommend that we maybe plan some more meetings and more on the technical level, to where once the submittal comes in, we have an opportunity, if you don't mind, to where we can sit down and go over the various different areas, and then there probably are going to be some longer meetings with some more in-depth questions about these things. I also think maybe we need to reach out to the regional people as well.
We will address those kinds of things once we see the submittal. I'm not sure that they'll be necessary. I kind of doubt that they will, but we'll see where we go.
But I see that, so I'm going to try to stop asking questions so much that you guys can get through your presentation this time, but don't take it as a lack of interest.
And we recognize that you're getting a lot of information, you're getting fed with a fire hose right now, but we also want you to be able to have this presentation will be left, and we'll take your time and go through it, and surely we'll be able to, and are happy to meet with you as we need to further this review process as it goes down the road.
Yes, we very much welcome the feedback. With that being said, I will go a little bit faster through some of these just to make sure we get a flavor and an overview, and we'll give kind of a 30,000-foot view on some of this to make sure we allow time for some feedback. So two-part 100% solid epoxy, an important component is that these materials don't have any VOCs, so there is not organic cartridge respirators that would be necessary on this project. You can see the primer goes on the pipe wall, followed by the additional materials that would be utilized. Here shows a kind of a close-up of the glass and carbon fiber composite. And we talked about how they would be used with the carbon fiber for structural strength, the glass for the dielectric and water tightness. A very important component is making sure that you have the appropriate qualifications and for the materials themselves. So we have an NQA1 program which has been audited by Dominion, and our epoxies and carbon fiber materials will be manufactured as a QA Category 1 in accordance with 10 CFR 50 Appendix B and ASME and NQA1. So briefly, the concept is that the materials, there's a comprehensive process that controls their manufacture, storage, and installation. And we would make sure that each one of those steps along the way have the appropriate procedures and protocols that would be in place for this application. Including making sure that there's qualification testing at the component and end state levels. The design approach would go to Rasko Ordzovich from Civic.
My name is Rasko Ordzovich, and I'm with the Thermal Stimson Jumper from Hager, consulting engineering firm, and we are designing the CFRP repair for pipe. We are designing the CFRP repair for projects with different types of pipelines. I'd like to briefly go over the design approach, and this first slide simply says that CFRP lining is designed as a standalone system in this particular application. We need that it takes the...
Speak up, please.
You see the...
Hold on, Jim. Let's try and move that a little closer to it.
Sorry. That was an 86. So the CFRP liner is designed to take all the loads acting on the pipe. In this case, in this particular case, the loads are obviously the internal pressure, internal negative pressure, and from the external loads, the pipe is encased in reinforced concrete. The reinforced concrete is assumed to seismic loads, it takes the live loads, gravity loads, and so forth. So CFRP in this case does not take the swirl loads, and this would be the case in all other buried pipe applications. in which we can take some concrete. We have touched on the question of two things. One is maybe CFRP adherence to the post pipe, and the other one is the transition to the post pipe. We go back to the pool. So in this case, there has to be some minimum level of adhesion to the hose pipe throughout the system. So the entire pipe is prepared by sandblasting and it's prepared especially well at the end region. So in this case, on the right-hand side, it would be close to that flange, let's say for the sake of argument, a foot of length next to the flange. And on the other side, it's also end of the installation. That's where it's prepared especially well to SP10 near the end. And in the middle, it's also prepared, but not to that level of surface preparation. So it takes all the loads, and at the end of the where it interfaces with the remainder of the piping system, that's where all the longitudinal loads and hoop loads have to be transferred from CFRP to steel pipe and vice versa. So that's where the good adhesion between the CFRP and the hose pipe is absolutely necessary in order to be able to transfer the loads.
Do you have any failure experience on the transition interfaces?
On the transition interfaces, there was one in a pre-stressed concrete cylinder pipe where the transition was not prepared to the current standards and to the level of preparation that was necessary. And I will discuss the evolution of the CFRP repair design procedure. The most important part in it is this research project that our firm had with the Water Research Foundation, in which we did some full-scale testing, lab testing, and the purpose of it was to identify and recognize the failure modes that the CFRP repair pipe can experience, and then to design against these failure modes. So one of the recognized failure modes was the bond at the end of the repair region, and that resulted in the development of procedures for design in that area.
One thing before we continue, just to head back to that point, we'll talk a little bit about OE on a future slide. It's important to note that the project team that's here has not had any failed CFRP installations. We have had between us several hundred successful carbon fiber installations. There are failures within the industry. There are some failures in the industry. And we have gone through and made sure to identify the motivation for those and how they've been appropriately addressed. And we'll be covering that in future content.
So if we can go on to the next slide. This research project was done for the Water Research Foundation, and it serves as a basis in development of the American Waterworks Association standard for design of CFRP repair of pre-stressed concrete cylinder pipe. That's a different type of pipe than steel, but nevertheless the pipe, and there's a lot of similarities when it comes to designing repairs for steel and PCCP. So it is. It included hydrostatic pressure testing of pipes, so we can see in the picture some 54-inch and 48-inch pipe that were tested essentially to failure. So over there in the pictures, you can see that the concrete core and pre-stressing wires were cut, even the steel cylinder was cut in some cases, so that practically CFRP would be the only thing taking the internal pressures. And other types of tests that were done were the 3-edge bearing tests. Those were the tests to simulate pipe installation in soil. So this would be a parallel plate test that's subjecting the pipe to bending with the purpose of, again, identifying the modes of failure. And in the lower row of photographs, you can see how the hose pipe is completely cracked, how CFRP is debonded from near the cracks, and so forth. Again, the purpose is to identify the failure modes and to design appropriately to prevent such failures from occurring in the actual pipe installation. Other parts of the Water Research Foundation project included numerous finite element analysis of pipe-soil interaction where the pipe was repaired with CFRP and then the pipe degradation was simulated by reducing the stiffness of the host pipe and so forth. Very important component in design of CFRP repair of pipe is buckling analysis, because CFRP is typically a very thin structure, and in most applications it's on the order of a half an inch thick, maybe up to an inch or so. So if you look at a 96-inch pipe that has a half an inch or 3/4 of an inch CFRP, it is a very, very thin shell that has to be able to take the external loads, groundwater pressures, negative pressures from the inside, and so forth. So the buckling analysis becomes very important. And we did an extensive literature survey of various approaches to buckling analysis of buried pipes. This is a buried pipe, and it's completely different than buckling of a pipe in air, because it's in part loaded by soil and at the same time supported by soil. Now, in this particular case, for the repair of Surry pipelines, the pipe is encased in concrete, so the buckling is constrained, and the mode shape and the deformed shape of a buckle is such that it cannot penetrate through the outboard of the shape of the existing pipe. So it's a constrained buckling that we consider in coming up with the critical pressures that the CFRP repair pipe can support.
Do you foresee using an FEA as far as the basis for the analysis that you guys are going to come in with? Or do you have an FEA work as part of your submittal?
Well, we have not yet done FEA analysis of details, and if
my FEA expert starts walking out. Yeah, no problem. All right.
So in the past, in some cases, we have done FEA analysis of CFRP repairs of special details.
I was just asking if it was in the submittal about our resources, but go ahead. Keep going.
Answer that question, I think is no. Is that correct?
At this point,
We would expect that. I think it's going to be balancing everything. Yeah.
Okay, thanks.
Now, the next aspect of this research project was a better understanding of material and material properties. And the basic material properties that go into design are similar to a CFRP as they are for steel and other materials, and they are strength, modulus, and ultimate strain. And those are determined by making and testing panels, and you can see some pictures here of how the panels are made, how they're tested, and some failed tension test samples for the CFRP materials. It's all done in accordance with ASTM standards, and the material properties are obtained based on the ASTM standards. As I mentioned, one of the modes that was identified was the importance of good bond and adhesion at the ends of the repair. And As a part of the research project, we performed the analysis of the shear bond strength between the CFRP and the host steel pipe, or in this case, steel samples. And we examined the effect of surface preparation on that bond. So you can see in these pictures steel plates which were prepared with wire wheel by grinding, by sandblasting to SP10 and SP5 and so forth. And we tested them in shear as shown in that picture over there, and determined that the surface needed to be prepared by sandblasting in order to get the appropriate bond and in order to get the reliable bond. For example, by grinding, you can get similar bond strength, shear bond strength as by sandblasting, but there is a significantly greater variability in the results. So it's not as reliable to prepare a surface by grinding as it is to prepare it by sandblasting. So that led into a development of the requirements for surface preparation that can provide adequate support for CFRP. Now, these materials, as we mentioned, are thermoset, and the way that the repair is installed is that the CFRP fabric is wetted in epoxy, it's brought in rolls inside the pipe, it's unrolled, it's troweled and pushed against the pipe, and at that point it's still all wet, so it does not have any strength. So the important component of the entire process is the cure. So we needed to understand how does the epoxy that's used to bind the CFRP fabric cure, and we did some studies to precisely do that. So for example, this slide here shows the ASTM test by differential scanning calorimetry to determine the cure of polymeric materials, and in the next slide we show the results of one of our studies on the percent cure as a function of ambient temperature, humidity, and time to cure. So for example, if a pipe is at 50 degrees, there would be the dotted lines near the bottom. You can see that percent cure remains about 70 to 80% even after 120 hours. So the cure is very slow, and it may take weeks before CFRP at 50 degrees would reach adequate cure. An adequate cure is at 85% cure. That's when the cured CFRP materials have the mechanical properties of strength, modulus, and ultimate strain equivalent to those at final cure. And you can see that, for example, if you crank up the temperature to 110 degrees, then in a matter of hours, you can get to the cure of more than 85%. So
the moisture of the pipe before application?
Moisture of the pipe before application is very important, and you will see in one of the slides that Anna will be discussing later on, we monitor temperature and humidity throughout the installation and monitor the dew point so that the combination of temperature and humidity is below the dew point, so that there is no surface moisture that can affect the installation of CFRP. Another item that was identified was the water tightness of the CFRP fabric. If you look at the fabrics and the uniaxial, so it's almost like you're looking through your fingers. You can see small daylights in between. So each fiber bundle is saturated, and epoxy is filling those spaces between the fingers. But when that gets pressurized, there is a potential that small gaps develop, and that's where the water can weep. So to prevent that, we do that by designing an architecture of the CFRP layup to have both CFRP in two directions, and also to include a glass fabric within the layup to essentially provide a watertight laminate that can take up the pressure. So to do that, we have developed a test chamber, which is the chamber that you see here, and it's designed to take up to 500 psi internal pressure. And in the middle, you can see within those four little quadrants in the middle, that's the CFRP that's exposed to the air. So there is nothing resisting water in the chamber other than the CFRP fabric over there. And this particular one is curved to a 96-inch diameter of the sample. So the tests involved fabricating the CFRP samples and then pressurizing the chambers and observing whether there is any water that comes out of or through that laminate or not. And I just want to bring to your attention the conservatism in this test is also in the boundary condition, because the boundary condition is that it goes from the stiffened steel plate, which is just about as rigid as it gets, much more rigid than any pipe that CFRP can be installed in, to an area where CFRP is the only thing that's taking the pressure. So, for example, in the left-hand side picture, you can see a very light layup. I think that this was a layup with one hoop, one longitudinal, or something like that, starts to weep at about 150 psi, and you can barely see the drops of water. On the right-hand side picture, there is a layup that went up to 400 psi, and it included the water tightness layer, which was essentially a layer of glass fabric. So just a 400 psi on a foot-by-foot window, that's about 64,000 pounds that's being supported by that 1 foot window of carbon fiber fabric. And the reason for this test was also to simulate the potential future degradation of the host pipe, because when CFRP is installed, pipe is more or less in good condition. It can have some pinholes or some holes and things like that, but it most likely does not have a foot-by-foot opening. But in the future, the hose pipe can continue to degrade, and this essentially simulates that down the road condition where the pipe or portions of the pipe no longer exist, and we have the CFRP bridging from the pipe that's still there, steel pipe that's still there, and steel pipe that's no longer there. So
I'd like to point out that Surry maximum pressure is 25.
yeah, the maximum pressure is 25 psi. So
That's right.
yeah. So
And that's right. Design is 25.
So all your accident conditions are 25.
For this particular system, it's just a canal load. We don't have a pump. It's all ground out there.
Okay, excellent.
Tremendous conservatism is built in from the process.
yes.
Another question with regard to differential thermal expansion between the pipe and the CFRP, or the...
Are you going to get to the end connections and
Not in that detail, because the way that I've structured it, I'm discussing some of the circumferential cases, but not longitudinal, but I would like to address this now. This may be a good appropriate time to do that. Temperature is one of the main loads, and the coefficient of thermal expansion of carbon fabric is significantly different than that of steel. And that is considered in designing the end termination. So in the end termination design, the parameters that we have is obviously the bond strength between the CFRP and the steel pipe, and that is given a surface preparation. So the only parameter that we have to design and play with is the length of bond. And that length of bond is designed to take all the longitudinal loads that can act on the pipe, and those include, for example, temperature, Poisson's effect from radial expansion, hydraulic thrust from bends and elbows and things like that. So all of those are taken into account in designing the end termination detail.
So all
So is the brittle failure mode not considered during the design?
Which one? I'm sorry.
Brittle. So this is not subject to brittle, this type of material?
Oh, and brittleness?
Brittleness, is it brittle compared to, have you considered, is the material brittle under a load?
The material is linear elastic, and the strength of this material is very high. It's in the hundreds of thousands of psi. So
I'm not talking about ductility point of view. I'm talking about the brittle point of view.
Yes.
Your material. So your material is not subject to the brittle failure you try to tell me. Well,
it would be subject to the brittle failure if you were to look at those tensile coupon tests. Those are potentially brittle failures of the material. So, for example, these tests here. But these failures occur at strains which are, let's say, 1% or even above. And the strain at which the pipe operates, or the design strain, may be on the order of 0.2 or so, or 0.3. So there is the range within which the load the CFRP are such that the strains are much lower than the ultimate strain of the material.
You talking about, I'm not quite sure about this one, but usually from the steel pipe point of view, you're brittle.
Oh yes, as compared with the steel pipe, definitely it is a brittle pipe.
And usually this brittle has nothing to do with the pipe size or anything. Just based on the purity. So you mentioned everything, okay, based on purity from the spectrum. So from the ductility point of view, right? You're not from the pressure toughness point of view.
Well, we first have to see what are the stress concentrations and voids that would result in stress intensity factors, and in the round pipe in which we are wrapping everything with CFRP, there really are no cracks to start it.
There's no crack at all. The crack is never going to start, and the crack is never going to grow at your point of view, correct?
Well, no, I'm not saying that there is no crack at all and that no crack will ever grow, but we have not yet seen any cracks that will grow here. So can you tell me?
You might want to address.
I may not be understanding your question
You want to
completely.
address crack initiation and crack propagation, or
Okay.
the potential therefore in your submittal.
To say, before we get into that, I think there's just some fundamentals, like composites don't crack like steel.
That's correct.
All.
Yes.
So there's some learning we need to do too, and we're just not familiar with it. And so we're gonna need some help with that for sure. It's a very different failure mode.
Yes, it is. That's completely different. Yeah.
You can't use the same design philosophy of steel that you would use for composites. The majority of composites are used for aerospace structures because they have extensive fatigue cycling, and the reason for that is because they are extremely good in terms of.
So addressing that in your submittal would be an appropriate thing to do.
When you're laying out all your tests,